Hello everybody and welcome back to page 114. So in this video we'll be looking at example 1. Let's read this together. So they'd like us to prove that phi going from z to z3 defined by phi of a equals a mod 3 is a ring homomorphism and to find the kernel. Okay, so let's start with proving that this is a ring homomorphism. If we scroll up and just sneak a peek at our definition, showing that this is a homomorphism is to prove that it preserves both the addition and the multiplication operation. That's where we're going to start. All right, so our domain is z, so we'll start with two numbers that are in z. Okay, and we'll start with the addition operation. So what would happen if we took phi of a plus b? Okay, well, according to the definition of our function, which is sitting up there, that's going to give us a plus b mod 3. And now we're going to go way back to some facts that we know about how modular arithmetic works. A plus b mod 3 is equivalent to a mod 3 plus b mod 3 mod 3. What we've done is to replace a and b by the remainders modulo 3. Okay, way back early on in the course, you maybe did an exercise or talked about this in class, how that's equivalent. It's going to give us the same result. Okay, and I claim that what we just wrote down is exactly equal to phi of a plus phi of b, which would finish the proof of the preservation of addition. Now let's think about that just to be sure that that's really true. Okay, so phi of a is equal to a mod 3 and phi of b is equal to b mod 3. So you might be thinking when you look at this that we need to get rid of the mod 3 in order for this to be a true statement. But actually that mod 3 at the end needs to be there because this addition operation that you see right there, remember that that's addition not of integers but in z3. So when you add two numbers together in z3, you're going to add them together. That's the a mod 3 plus the b mod 3. But then at the end, you need to take mod 3. Okay, that's what tells us that we're doing addition in z3. So it actually is exactly equal, okay, with the mod 3 on the end, like we see it. All right, let's clear a little clutter away here. Okay, so we do need that mod 3 at the end. Okay, and so reading this left to right, we started with phi of a plus b, we ended up with phi of a plus phi of b. We've proven preservation of addition. Okay, so let's move on then to multiplication. This is very similar. So phi of ab, by definition, looking back up at the top of the page of our formula, that would be ab mod 3. And we can replace a and b with their remainders mod 3. So this is equal to a mod 3 times b mod 3 mod 3. Okay, and in the same way as we discussed above, that last expression is going to be equal to phi of a times phi of b. That's just the multiplication of phi of a times phi of b modulo 3. Okay, so that proves that phi is a homomorphism. Okay, we showed that it preserves addition and multiplication. Okay, so what we're down to then is the last part of the question, which asks us to find the kernel here. Okay, so the kernel, again, just sneaking a peek up here, is the set of all inputs that map to the additive identity such that phi of r equals 0. So let's do some algebra and see if we can figure that out. We'd like to know what are all the solutions to the equation phi of, I'm going to use the variable, or the letter a here. It doesn't really matter, but okay, we want to know what are all the a's such that phi of a equals 0. Well, phi of a, by definition, looking up here at the top, is a mod 3. Okay, so this expression right here. So we'd like to know what are all the values of a such that a mod 3 equals 0. If you think about that, you're going to get 0 anytime a is a multiple of 3. Okay, and that tells us then that the kernel is all integers such that all integers that are multiples of 3. All right, and so we get kernel of phi equals, make a big long list of all multiples of 3. So -6, -3, 0, 3, 6, and so on. Okay, and we could also write that by noticing that the set of all things that are generated by 3.